Welcome back to the Curious Mind GATE-2013. In this video, we are going to learn about which numerical integration scheme or technique is associated with what order of fitting polynomial. In other words, we are going to learn about which scheme of the numerical integration is derived from what order of fitting polynomial. Using this question, which is from GATE 2013 ME Set A, which asks to match the schemes of the numerical integration with their corresponding order of fitting polynomial. That is, this question asks about to match these numerical integration schemes with their corresponding order of fitting polynomial. Alright, in other words, we will determine the rule of the numerical integration technique based on the order of the polynomial that approximately fits the curve of the function in each of the subinterval, which we will have when we draw the diagram of an arbitrary function and divide the area between its curve and the x-axis into equally sized vertical subintervals over the domain of the function. To begin with, I would like our viewers to first recall that each numerical integration technique is a form of a integration technique that does not directly calculate the exact value of a definite integral. Rather, it helps in determining the approximate value of that definite integral by dividing the area under the curve of the function of that definite integral into many and small similar shapes which are approximated of a specific known type, either rectangular or parabolic or any other specific geometry, and then adding the areas of those small shapes gives the approximate value of that definite integral. As we all know that the definite integral of a function from one limit point to another limit point is equal to the area under that function between those limit points, or more precisely say, the area between the curve of that function and the axis along which the limit points vary. For the simplicity, in each numerical integration technique, the total gap or the interval between the lower limit and the upper limit of a definite integral is divided into equally sized small subintervals. And the main reasoning behind each approximate definite integral technique is that the complex shaped curve of a function is approximated into a simple curve such as a horizontal or inclined line, a parabola, or a cubic function in each subinterval, resulting in different numerical integration techniques, and be sure can easily determine the small area under the simple curve in each subinterval, and finally the sum of those small areas under approximated simple curve in each subinterval gives us the approximate value of the definite integral over its entire interval. Now, before we move to the next page and draw a diagram of an arbitrary function, I would like to highlight this line. The main reasoning behind each approximate definite integral technique is that the complex shaped curve of a function is approximated into a simple curve such as a horizontal or inclined line, a parabola, or a cubic function in each subinterval, resulting in different numerical integration techniques. Now, let's consider an arbitrary function phi equal to fx, which can be defined in a domain from, let's say, x equal to a to x equal to b, and draw it in the xy plane. There we have it. Now, the value of the definite integral of fx from x equal to a to x equal to b would be the area under the curve of the function fx, right? So this area from x equal to a to x equal to b and between the curve of the function y equal to fx and the x-axis is the area, right? And which is equal to the definite integral of the function fx from a to b, as we have explained in the previous page. Now we would divide this total area into, let's say, three equal parts, and the total area can be divided into any number of parts, but we would divide it into equal three number of parts for the illustration purposes. So we have divided this total area into three equally spaced subintervals with each of width h, which is equal to b minus a divided by 3, right? Because b minus a is the total width of over which the domain of the function fx varies, and we considered three subintervals, and each subinterval we approximate that the portion of the curve between its endpoints is a simple curve, not the curve of the function fx. Meaning, we assume that this curve, which is of the actual function fx, is a, is a is a simple curve, right? Between the endpoints of the interval, and this simple curve is a one that we know, all right? So in each interval, all right? So this will be for each interval. Now, if the portion of the curve is assumed to be a horizontal line, right? Like these, all right? So what we did here is we assumed that the the curve of function fx is approximated into a horizontal line, all right? This, which can be equivalent to a polynomial of order 0, right? Because this horizontal line, the equation of this horizontal line, or these horizontal lines, is always equal to y equal to constant. So y equal to constant means the order of the polynomial would be 0, all right? and and we would have rectangles in each subinterval, and the corresponding numerical integration technique becomes a rectangle rule, or say midpoint rule. So basically we replaced this curve of the function fx with a y equal to c1 uh, for this interval, and we replaced y equal to fx with y equal to c2, right? Where c2 and c1 are constant in this interval. Similarly, we replaced this curve for this interval with y equal to c3, where c1, c2, c3 are all constant, and the curve that is approximated is a polynomial, right, of order 0, because we know that y equal to constant is a polynomial of order 0. And this type of assumption where we changed or approximated this area under this actual function y equal to fx between this interval into a simple area of a rectangle. All right, so we approximated this total area means this area for this subinterval into a area of a rectangle. All right, and we did the same here and here. So this sort of approximation where the total area which would be between x equal to a and x equal to b and between fx and x-axis can be approximated into the sum of the areas of all these rectangles. All right, so the total approximated area would be equal to the approximate value of the definite integral of the function fx from a to b. All right, what that means is that the sum of all these areas of rectangles would be equal to the approximate area or approximate total area, and this approximate total area would be equal to the approximate value of this definite integral. On the other hand, the total area under this yellow curve between this limit x equal to a and x equal to b would result in the exact value of this definite integral from a to b. But in case of approximated total area, by replacing or approximating this actual curve with the assumed curve, which in this case are the horizontal lines, then the resultant areas are the areas of the rectangles, and their sum would result in the approximate total area, and that would be equal to the approximate value of the definite integral from a to b. Now, this would result in the numerical integration technique. In other words, this is what the numerical integration technique means. That is, approximating the value of the definite integral using the approximate total area. Alright, that's what the numerical integration technique means. So, this numerical integration technique is, is called rectangular rule or midpoint rule. Similarly, if the portion of the curve y equal to fx in each interval is approximated into a inclined line, all right, instead of a horizontal line, and then that would result in a different numerical integration technique called trapezoidal rule. because in that case we would have a triangle and a rectangle. Alright, so let's draw that setup. There we have it. We have replaced the horizontal lines which we assumed the shape of the curve, and in this case we can approximate the shape of the curve pi equal to fx with an inclined line which is different in all three subintervals, but they are all and inclined lines with different equations. So we can approximate this curve pi equal to fx into an inclined line with an equation given by this, and for this subinterval by this, and for this subinterval by this, where C1, C2, C3, C4, C5, C6 are all constants. All right, and we know that the order of a polynomial of a straight line in the form of y equal to c1 x plus c2, the order of this type of straight line for a polynomial would be equal to 1. All right, so the order of a polynomial of a straight line is equal to 1, and the corresponding numerical integration technique becomes a trapezoidal rule. Why? Because here in each subinterval we have a, a triangle which is a right triangle and a rectangle. Right, because we know that a trapezoidal is made of a triangle and a rectangle. Right, so we here in this numerical integration technique, which is a trapezoidal rule, we approximated the area under the curve in each subinterval into an area under a straight line between that subinterval. Alright, so the total area would be the approximate area of the sum of all three areas under all three different straight lines. Alright, and finally here we would get the approximate value of the definite integral of the function f(x) from a to b using this numerical integration technique, which is a trapezoidal rule. Now similarly, if we replace this straight lines that we assumed the shape of the curve with a, let's say, a parabola, right? So these straight line would be replaced by parabolas, right? And we would assume those parabolas into a curve instead of the actual curve, which is equal to y equal to fx, right? To approximate the area into area of these subintervals. So let's replace these straight lines with the parabolas. So if the portion of the curve of the function fx in each of the subinterval is assumed to be a parabola, which is drawn in the blue color. Then we would have an area under the parabola in every subinterval. Now, the equation of these parabolas would be different in each subinterval. So, the corresponding numerical integration technique would become a Simpson's one-third rule. All right. Now, and we also know that the order of a polynomial with an equation given by a parabola would have the value of 2. All right. So, the order of a polynomial with an equation of parabola would have order 2, and the corresponding technique becomes a Simpson's rule. Similarly, if the portion of, of the curve in each subinterval is assumed to be a, say, a cubic function, right, which is drawn in this blue color, then we would have a area under a cubic curve in all the in every subinterval, and the corresponding numerical integration technique becomes Simpson's 3 by 8 rule. All right, and we know that the polynomial with an equation of a cubic function would have an order equal to 3. All right, so just to summarize, if the portion of the curve is assumed to be a horizontal line, which is also a zero order polynomial, then we would have rectangles in each subinterval, and the corresponding numerical integration technique becomes rectangle rule or midpoint rule. Now, if the portion of the curve is assumed to be a inclined line, which is also a first order polynomial, then we would have a combination of a right triangle and a rectangle, right, in each subinterval, which is a now the combined shape of those triangle and the rectangle would be a trapezoid in every subinterval, and the corresponding numerical integration techniques becomes a trapezoidal rule. If the portion of the curve is assumed to be a parabola curve, which is also a second order polynomial, then we would have a area under a parabola in every subinterval, and the corresponding numerical integration technique becomes a Simpson's one-third rule. And if the portion of the curve is assumed to be a cubic function curve, which is also a third order polynomial, then we would have a area under a cubic curve in every subinterval, and the corresponding numerical integration technique becomes a Simpson's 3 by 8 rule. Therefore, based on the numerical integration technique, that we choose to solve a particular definite integral problem, our assumption of the shape of fitting of the curve between the endpoints of each subinterval changes, right? So what does that mean is that based on the numerical integration technique or its rule, right, the assumption that we assume changes, all right, that what type of curve that we would assume instead of the actual curve of the function fx, right? Now let's go to the first page and try to answer our question, which is this. So the Simpson rule, one Simpson's 3 by 8 rule is associated with a polynomial that would fit the with our curve that we explained earlier, and the order of this polynomial would be third or 3. And in case of trapezoidal rule, the order of the fitting polynomial would be 1 or first, right? And in case of Simpson's 1/3 rule, numerical integration technique, the order of the fitting polynomial would be a second order fitting polynomial, because second order fitting polynomial is a parabola and third order polynomial is a cubic function and first order polynomial is a straight line. All right, so the valid option is option, right? So this is the correct option.